It is more than university, actually. It's like it's more familiar already now, and I'm really glad to share with you what we do have over here. So our department of physics is rather young, let's say so. Yeah, 10 years ago, we started like 10 people, and we, actually not we, our supervisor, Pavel Belov, he won a mega grant together with Yuri Kevshar. And it was a small laboratory under Yuri Kevshar's supervision. And since that time, we became we were growing more and more, we employed more and more people, we started new directions, new scientific research directions, and now we are already Department of Physics, and we are more than 300 people, and the average age is roughly 20 years old of our employees. It's mainly because of the students who works with us, and they are really deeply involved in the scientific tasks over there. So at our department, we do have a really big number of scientific projects. Yeah, we work in the MRI, we work in the perovskite nanophotonics, in 2D materials, we investigate metasurfaces in microwave, in optical band. So we do some radio physics as well, and some drug delivery, some topological photonics, optomechanics, dielectric nanophotonics, microfluidics, a lot of the directions, yeah, and you can take a look at the web page, what we currently do in all this wide range of research. So regarding the radio physics, yeah, we do have some facilities which are in our building, yeah, and this is the photographs of the microwave chamber, anechoic chamber, which we have created so far. So it is roughly 4 by 5 by 9 meters anechoic chamber. We can do antenna measurements, and we can do some near field scanning, because we do have a 3D scanner over here which can measure the near field profiles probably around the sample in all the 3 directions, X, Y, and Z. So we are quite good equipped with the vector network analyzers and other equipment in order to proceed with this measurement. So we are open to any kind of collaboration in terms of the antenna measurements, in terms of some testing, probing, any kind of this stuff. So if you're really interested to do something, please contact me, and we will definitely proceed together. So our main outcome, let's say so, is the publication, yeah, and our members, they publish quite a big number of papers in the high-ranking journals, and here you can see some small statistics, yeah, with respect to the number of publications around the years, and with respect to the impact factor of the journals, and we are really proud of this activity of our researchers. So let's now speak more about the main idea of today's seminar. So I will roughly start with the motivation, then I will demonstrate some modern approaches of wireless power transfer systems. Then I will show you 2 prototypes based on the Metasurface-Inspired Resonators. It is smart demo, smart table demo, and their chess demo, and then some words in the conclusion. So wireless power transfer technology appears a couple of years ago. It was like a renovation of this technology, yeah, when the market was growing, yeah, and we have a lot of electronic devices which need to charge their batteries, yeah, and now this technology has already found the application in charging of mobile phones, for example. Yeah, a lot of efforts are done in order to charge vehicles, and for instance, we can charge any consumer electronics on body electronics using this technology. Yeah, I mean that this technology is really our future, and it is a really fast developed approach which finds the application already now. And now market demands not only charging of one device from one transmitter to one receiver. Now market needs to charge many devices simultaneously. Yeah. So, and my main idea how to create the system which will be capable to charge several devices at once with high efficiency, with safety, with comfort for the user. Regarding the methods, yeah, which methods can be used in order to charge the devices? So inductive various power transfer, yeah, probably proposed by Nikola Tesla many years ago. Yeah, when we do have two coils, and there is a current in one coil, some induction, and the current appears in the second coil. So very simple approach. It is used now in order to charge mobile phones. Yeah. But the main limitation is the distance. You need to locate the transmitter coil and the receiver coil very close to each other in order to get high efficiency. Yeah, and also some misalignment problems and so on and so forth. However, this method can be applied. Yeah, it's already the reality. In 2007, it was proposed the method for magnetic resonance power transfer. The difference is that together with the coil, we do have a capacitor. And we do have a resonance in this transmitting system or resonator, yeah. And as soon as we have a second same resonant part receiver, yeah, the channel for the various power transfer is open, and again we transfer the power using the magnetic field, which penetrates the transmitting coil and receiving coil together. It helps to increase the distance. This method. So as soon as you use two resonators, you can increase the distance of various power transfer drastically, and it is the really good approach in order to create the modern systems when you need to operate rather far away. So another method is to use the capacitive power transfer. So here the power is transferred using the electric field, and this field is concentrated between two electrodes. So the first electrode is the transmitter, the second electrode is the receiver. So some distance in between. Everything works good. It was demonstrated this approach can be applied for the high power applications, so like 3 kilowatts probably, and so on. But as soon as you operate with the electric field, it is more dangerous for the biological objects which are situated next to the system, yeah, because we do have some influence of the electric field. And with the magnetic field, the system is kind of safe, yeah, if you concentrate the electric field in some proper area. So again, capacitive method can be used as good as you want to transmit the power not to the large distances. Again, if you speak now about far field, about the transferring of the power to the really large distances, yeah, we need to work with the far field approach where the power will be transferred through the propagating waves. Yeah, mainly some antennas, very directive antennas, in order to transfer the power to the large distances and so on and so forth. So this method is more or less okay, but it suffers from really high losses, and the efficiency of this method is not really high. So if you are ready to lose mainly 99% of the power somewhere on the way, then please move on. It's okay. So here are the examples of some prototypes of such systems used where we use this, let's say, standard classical approaches: inductive, resonance, and another type of the resonance, various power transfer. So what people do in order to charge multiple devices, they can combine, for example, two coils. One of the coils operates at kilohertz band, another coil operates at the megahertz bands, depending on the standard, yeah, and it is possible to charge several devices at once. Okay, could be. Another approach is to use a resonant coil and allocate all the receiving coils on it, yeah, but then you need to play with the signal somehow in order to provide high efficiency at all the receivers over here. And this approach is quite nice, so you don't need a planar resonator. You can create a volumetric resonator, yes, some kind of a metal box, and excite some eigenmodes of this metallic cavity, and transfer the power to the receivers which are allocated inside. So that can be a good idea, but I'm not sure that we would like to be blocked in the metallic box somewhere, yeah, if it's your living room or your office or somewhere else, yeah, but okay, this is also the idea. So what's actually new we can get from the 21st century, because we are now providing a lot of the progress in different fields. So we can give some different approaches in order to increase the efficiency or extend somehow the characteristics of the systems. So we can use coherently enhanced various power transfer, and there's really good work by Alexander Krasnov about that. We can use some exception points, parity time symmetry-based system, or we can use the approach of on-site generation. Yeah, this is new ideas which were applied to the deputy techniques. And probably the main idea which I focus on is the use of metasurfaces in order to enhance the functionality of the various power transfer systems. So what is the metamaterial? I'm pretty sure you have heard about this term, yeah, and probably a little bit familiar with this. Here's the classification of the materials. So some natural materials, they have a positive permittivity and permeability, yeah, and we all know how the wave propagates over there, yeah. It's classical approach, which is well known. So roughly 15 years ago, people have started investigation of metamaterials where permittivity and permeability are negative. So they call them metamaterials because it is something which is not available in nature, and this something provides you some unique properties of the wave propagation. So it was probably the classical definition of the metamaterials for the 15 years ago. So what is going over here? So for the classical medium, we do see how the wave propagates. In the medium, we have a wave vector and pointing vector co-directional. So if we do have a metamaterial over here at the interface, we see really different wave propagation manner because of the negative refractive index. And we do have wave vector and pointing vector not co-directional, they are in the opposite directions. It was really widely investigated. A little bit later, people understood that we can have only one of the material parameters negative, epsilon or mu negative, yeah, and those media will also provide a lot of interesting effects of the wave propagations. And again, people constructed a lot of different types of the metamaterials. They have established different effects over there, confirmed the theoretical predictions made by Vesilaga, and so on and so forth. So it was like a boom in this area, but it was like 15 years ago. And now people are mainly interested in the metasurfaces. Yeah, metasurface is this two-dimensional analog of a metamaterial. So metamaterial is bulky, and you need to create rather big piece of metamaterial in order to get the proper effect of the wave propagation. So in case of metamaterial, you need only the slab, rather big in the dimensions, in X and Y dimension. However, it will be thin. Yeah, and again, it is engineered media or engineered slab. And the unit cells of the metamaterials are specially designed in order to get these unique properties which are not found in nature. Yeah? And what you can actually do with the metasurfaces, you can do a lot. You can do kind of filtering, you can do some kind of bend stop, or you can create some perfect absorbers, you can control the polarization of the wave, you can convert the polarization, yeah? You can create some leaky wave antenna, focusing or defocusing arrays, and so on and so forth. Yeah, it is quite a big number of applications of the metasurfaces in the wave propagation field, yeah, people are really interested in bringing them to the new technologies which we do have already now. So a lot of efforts have been done also in order to use metasurfaces in the various power transfer systems, metamaterials and metasurfaces, but mainly people did something like this, yeah? They installed a metamaterial, a metasurface in between of the transmitting and the receiver coil. So in this case, this metasurface works like a lens, which is collecting the transmitted signal and focus that to the receiver part, yeah? You can allocate the two metasurfaces probably. You can put them on the back sides of the transmitter and the receiver coils in order to create to cancel the backward radiation, yeah, and concentrate the signal away in between of the coils over here. So this works, and you can see here the example where we see the valve is shining in the presence of the metasurface lab. Yeah, and this is just not really good shining when the metasurface lab is absent. But again, for the practical application, it seems not really good because you still need something in between of the transmitter and the receiver. Yeah, something in between or something next to it. Yeah, that's why we do proposed another approach. We would like to use the metasurface as a transmitter itself. And we believe in the idea of the smart cable as a device to charge many receivers at one transmitter. So in fact, the metasurface can be incorporated or placed above the table, and all the electronic devices which are situated on it can be charged wirelessly, simultaneously over here. What we need to do in order to get it, yeah? So definitely we need to create a quasi-uniform magnetic field distribution. Yeah, we would like to operate with the magnetic field. We would like to use this magnetic resonance for transfer method, rather uniform magnetic field over the area of the table. We need to drastically reduce the electric field because we would like to make the safe system for the people around. And this device should operate at the lower frequencies in kilohertz or megahertz band. So maybe ISM band could be okay for that. It would be also good if the Metasurface or Metasurface-Inspired Resonator would operate in the multi-mode regime where we have several operating frequencies and we can adopt them to the existing standards, for example. Yeah? And here is the main idea of our smart table operation. So you can see here the multi-conductor transmission line, and it is from the microwave approach, from the microwave transmission line approach. The idea is coming from over there. So you do have a section of the transmission line, and if the electrical length of this transmission line is proportional to λ/2, yeah, then you do have this field profile distribution. You do have a maximum of magnetic field in the middle, and you do have a minimum of electric field over here, and the maximum on the edges. However, if we estimate the length of our transmission line operating at kilohertz or megahertz band, yeah, then you will see there's several kilometers or something like that, and of course it's not practical for our use. So what we can do, because we would like this region with the uniform magnetic field distribution in order to charge devices, yeah, but we need to minimize the system. We can load that by capacitors and truncate the undesired piece of the wires over there. So in this case, you keep the electrical length of this line the same, λ/2, but the physical size became much, much smaller. So now we do have this type of system, several wires loaded by the capacitors, and it seems that we kept this region with the uniform magnetic field distribution, and at the same time we can find the electric field on the edges of the structure. Here you can see the dispersion diagram of our system. If you can calculate on the unit cell, you can see that the frequency will decay with the mode order. And traditionally, in the transmission line, the frequency increase. Yeah. In our case, we do have higher order modes at the lower frequency. That means that we do have a so-called left-handed transmission line, which is the part of metamaterial approach. So we do have, let's say, negative dispersion in this case. And that's why I call this Metasurface-Inspired Resonator. We do have some features of the metamaterials or metasurfaces over here. I fabricated this prototype. So we use the standard PCB technology in order to etch the wires. We have put here on the edges the capacitors, yeah, as SMD components, and we have verified this system in the megahertz frequency band. You can see that we do have several modes which are excited in our structure. The distortion is negative because the next mode, the higher order modes, appears at the lower frequencies. And here is the fundamental mode, which is mainly interested for us because it has a rather quite uniform magnetic field over the area of the resonator over here. At the second mode, we do have two maxima of the magnetic field, which actually could be also used on device for transfer as well. And then we have investigated the efficiency of this prototype, only the ref efficiency. When we do have one receiver above the metasurface, above the transmitting resonator, yeah, we can provide like 80% efficiency at the first mode, roughly 85% efficiency at the second mode, and so on and so forth. And the main mechanism of losses is the losses in metal and the losses in the lumped components. We can still increase it using another materials because in this case, for prototyping, we use not really good materials here, and we can still improve that up to levels of 90%, 95% if we use another components and materials for the fabrication of this system. So our idea regarding this approach of the Metasurface-Inspired Resonator works. We do have rather quite uniform magnetic field distribution, and the system operates in the megahertz frequency band. Here we can see some demo. Yeah, we attached this resonator to the power amplifier, and here you can see some tests already with the receiver and some kind of a load. The LED is a load, and here we just confirm that we work on this quasi-uniform magnetic field profile, and the LED is shining over the whole area over here. Also works for the multiple receivers. So for the multiple receivers, yeah, and as soon as the field is mainly oriented or mainly oscillating up and down, you can charge from the vertical oriented receivers at the fundamental mode over here. And we demonstrated we can charge several of them. But the second mode provides more functionality because you can charge as well as horizontally oriented receivers as well as vertically oriented one, because the field distribution is more complicated over here. Yeah, we do have two maxima over here and can charge multiple devices on it as well in vertical and horizontal locations. So it was just the testing of idea at rather high frequencies, roughly 17 megahertz, but following the standard, we need to adopt the system to 678 megahertz, so we did it. And we completed the Metasurface with the power amplifier and created the smart table prototype already in order to charge some electronic devices. So together with my colleague, I'm very thankful to the people who participated in this project. Yeah, we did really great job together using this modern approach in terms of the metasurfaces, and then completed it with the power amplifier design and collected everything in the one prototype. And you see the two mobile phones appearing at the smart table. They are started charging, and the efficiency now is not that high, roughly 40%. I speak now about DC-DC efficiency, so the whole system. And we still have some room to improve that in terms of if you will fabricate better power amplifiers, better matching networks, and so on and so forth. So there is still possible to improve that. And here you can see another demo, which we call modern chess or pair chess. And again, we used the Metasurface-Inspired Resonator in order to create it. And it is a transmitter, and we do have multi-receivers as a chess figures. Yeah, and you see they are shining with the green and blue color. Yeah, we do have this luminescence or shining effect or something like that when the chess figures are situated on the chessboard. So how we did it, yeah, and why they are shining. They are shining because we use perovskite quantum dots, and we do have this research direction in our lab. and colleagues who investigated the perovskite quantum dots, they came to me and they were very happy because they found a way how to create green and blue perovskite quantum dots. And they also studied how to incorporate those quantum dots in the polymetric matrices, yeah, because the quantum dots, if they are not protected, they degrade. Yeah? In a couple of days, you don't see this shining effect anymore. And they were able to incorporate it to some polymer resin over here, and they just told me, Polina, look, we do have really great quantum dots. We can insert them to the polymetric matrix. They will provide this shining, this luminescence effect as soon as they are irradiated by the light of a proper wavelength. So we need just to deliver somehow over there the power and light them up. And altogether, we came to the idea to create this chessboard as a first prototype where we merged two technologies, perovskite quantum dots and various power transfer. And it was just because it's really effective way to demonstrate these two technologies. Yeah, so that's why we decided to do chess. Guys have created these chess figures, incorporated the quantum dots over there, and we have created the receiver part, so it is inductance loaded by capacitor, then some rectifying stuff, and LED, which is shining at the proper wavelength, and as soon as it's shining, we do see the luminescence of the quantum dots. So without the LED, we would not see this blue or green color of the chess figures. So the transmitter is a Metasurface-Inspired Resonator, which was optimized to chi standards. It's roughly 200 kilohertz. Again, we do have wires, which are loaded by capacitors over here, and everything is incorporated to the backside of the chessboard. And here you can see the magnetic field distribution and some power distribution around the surface of the chessboard. We have measured these numbers, and it's quite enough in order to light up an LED over there. So as soon as you have a figure in any position of your chessboard, it will be quite enough of power to light up the LED. But very important question is the safety of this metasurface for the people who are playing in this game up to now. And in order to check the safety, we have calculated, simulated and calculated the SAR, specific absorption rate. It says us how many power is absorbed in the tissue. Yeah, and there are some limitations for that, some standards and limitation, and we can see with the metasurface we are safe, and we are better safe in comparison to the standard coil, which we could use as a transmitter in the chessboard. So let me conclude my talk for today. We have proposed an approach how to use metasurfaces in order to create the transmitters and use them in one-to-many various power transfer system. So we did this. We completed the system with some power amplifiers and so on and so forth. And I have demonstrated the demo of the smart table. And another demo which I have shown to you is the PeroChess prototype, which is operating at a really low frequency, and it is possible to charge 32 receivers at one surface simultaneously altogether. So thank you very much for your attention. I'm ready to answer your questions.
Thank you, Polina. Maybe first question from my side. As I understood, you create metasurfaces which are used as like something like static antennas, which help to radiate a magnetic field in some direction. Do you plan to make maybe not static but some dynamic antennas? For example, if you put your phone on one part of the table, you change it, so maybe you don't need, in fact, to radiate a magnetic field in all directions on the whole table.
Okay, yeah, good. It's a really good question. So I would not call it antenna, yeah, because we don't deal with the far field, we deal with the near field. We create a uniform near field profile. In this case, we don't have a losses for radiation at all. You can see it at this diagram. So we don't radiate anything to the far field. We just create a resonator which gives you this opportunity to control the near field. Control, I mean to create the uniform field at the fundamental mode and 2 peaks of magnetic field at the second mode. So you can probably switch the frequency or something like that. Yeah. The idea about your idea, yeah, regarding the shaping or controlling the wave propagation or radiation propagation, yeah, it also known in various power transfers. People do that. They track the receivers with the far field approaches, and it's a really good startup in US who did it already, and they work at the higher frequencies, roughly to 900 megahertz, in order to do that, and they use antenna arrays for that. They found a way how to optimize this antenna array and how to detect the location of the receivers in the room and so on and so forth. So it is just a little bit different approach, which I don't work so far. So I mainly work with the near field approach.
Okay, so you use low frequencies, so these approaches are not needed for low frequencies.
Yeah, this with the far field, the approach of operation with the far field better works at the higher frequencies.
Okay.
Yeah, because your antenna sizes at low frequencies will be really huge. Yeah, and you need just higher frequencies a little bit.
So thank you for your presentation. So if we consider this slide, you said that the efficiency at the third mode is the highest. Mm-hmm. So why don't we use the third mode for your prototype or, for example, multiple nodes for charging simultaneously? And because of the profile or what? So you demonstrated on the performance on the first mode and the second mode. What are the differences between the performance?
Yeah, like the mode profile is different. Yeah. At mode number 3, we do have the minima over here, and if your device is located probably over here, you'll miss some power. Yeah, you lose some power. You don't charge over here. Also, the mode profile, if you take a look to the magnetic field, so here's the metasurface, and here is the magnetic field, which penetrates at the fundamental mode. The field decay decays not that fast, so you have a bigger penetration of the magnetic field out of the metasurface. Yeah, it means that you can charge at the distance, far away at the distance from the metasurface as well. At the third mode, the magnetic field is more and more confined to the metasurface, and your distance, if you need it in the end of the day, yeah, from the transmitter to the receiver, where you will get rather effective coupling, will be smaller. But again, you're absolutely right. Probably someone needs that for the application, and they can use the third mode of the resonator as well. The second mode can be also used probably for smart table. Just imagine the situation in the office when you have a table for 2 employees, yeah, sitting face to face, yeah, and each of them has their own area where he can put some devices to charge them simultaneously. So we mainly focused on this mode, but of course we can combine the modes, we can switch between them in order to charge multiple devices and so on and so forth. Now we are doing some projects in order to have one mode in kilohertz band, another in megahertz, or get the even mode, or so like 678 and then 1356. Yeah, we need this cover to these 2 bands. Yeah, and we are optimizing our structures in order to further enhance the functionality.
Okay, thank you. So I have one more question.
Yeah, please.
Yeah. So is there any limitations for the number of devices on the smart table? For example, am I right that if you use, for example, 2 devices for charging, the time per charge will be twice longer than for 1 device, and so on? Or there are some more limitations for the number of devices?
Look, The limitation is the transferred power or input power. Yeah. The speed of charging of your device depends on the power level. Yeah. The more powerful level, the faster is the charging. We are limited mainly with the SAR, by the way. Yeah, because it is some limit under which you can apply the high power. So up to here, we tested for 5 watt, but we see that we can still increase the power level and stimulate more power and allocate more objects. Yeah, for the smart table, it will work in the similar manner. We did not test the limitations so far in practice. We used only 2 devices on it, but I'm pretty sure that we can put more. But again, efficiency now of the smart table is not that high. It's roughly 40%. So you lose more than half of the power. Yeah, you stimulate probably 40 watts in order to charge 2 mobile phones, which needs 5 watt. Yeah, and this is the question already. So this is the question altogether: efficiency, SAR, safety level, yeah, and probably the area of your device. You can design it in a little bit bigger in order to allocate like 10 devices and so on and so forth. So it is planned to check the safety. I mean, that safety has been checked for this particular device at this frequency. It is published in one of our works. Again, we do see the lower SAR than a coil, yeah, and we need to measure the safety probably already in this prototype, yeah.
Thank you.
Thank you, Polina, for coming here for an interesting talk. I have several questions. Let me ask these 2.
Okay.
So the first question is about safety experiment. So you have presented some results related to SAE, yeah. And what were the conditions of this experiment? Were there any power receivers when this experiment was carried out, or the board was empty without any figures?
Okay, I see.
So how the result changed when there are some power receivers and where the board is empty?
Look, we didn't measure it, unfortunately. We don't have such facilities up to now. We can simulate it in some software. So here is the here's the model of our metasurface, and you see that the electric field is mainly concentrated on the edges. Yeah, we put an arm to the maximum of the electric field, probably over here. Yeah, with respect to port. Here is the input port, and it is over here. Here, yeah, we put an arm in this region and calculated the electric field with the arm. And from the electric field, we calculated the SAR. So if you will put here some receivers, then it will be better story, because you do have some way for energy to leak. Yeah. So this is the scenario how we should simulate the SAR in order to estimate how dangerous it is for the arm. Yeah. So you will see probably the same numbers of SAR, probably a little bit smaller numbers of SAR if you will put the receiver over here.
Thank you. And the second question is that in any of the mode, you have an area, a green area when there is a very small power. And did you consider something like considering two surfaces rotated by 90 degrees to avoid this area? So whether it's possible to avoid, maybe using some different frequencies, so whether it's possible to avoid these blue areas.
Yeah, you mean this area? Yeah, it is really wet area, and we also observed with the smart table that over here the efficiency became even smaller, yeah, because it is not purely uniform magnetic field, it's still quasi-uniform. So we do have some ideas how to overcome this problem. We can do some non-equal distribution designs of the wires inside of the sample, yeah. And in this case, we can optimize the shape of the field. Yeah, but it really has to be done, and probably this idea with the rotation can also work. We also try to test it as well with our colleagues, and it can be done further.
Let me ask the third question. So, did you also study what happens with the far field if there are no receivers on the surface?
There is no far field.
So no emission outside, say, 10 centimeters or that level?
No.
Okay.
It's roughly, probably the magnetic field, at the fundamental mode, magnetic field penetrates up to 30 centimeters, probably something like that. But it is not far field if we consider the megahertz frequency band. It is near field.
Yeah.
So.
Okay. Thank you.
So, any other questions?
One question from me. Do you plan to produce some commercial, not prototypes, but products? So you said that you have developed the prototype of some commercial charging standard. So do you have any plans?
Yeah, we do have plans, and we do have interest from the several companies. One of them is Huawei, Chinese company, and we are in a process to do something together, to collaborate on this smart label design. The main limitation over here is that the operational frequency. As soon as we now work in the megahertz frequency band, there are not so many elements for the fabrication of the power amplifiers. You can use some Gallium transistors, but they are not providing really high performances for those tasks. And they are in the process now of investigation. So some components. We need better components. Probably we need to scale our Metasurface design to the kilohertz band, where we do have good transistors. And we did it with the chess in order to verify that. So more or less the same. We are now trying to fabricate the chess and sell them to someone. If someone interested to buy. So, but I believe that this approach of the smart table can be further incorporated to the reality if we will find the proper industry to do that together.
I think you can raise money using Kickstarter.
But again, there are some first steps in this direction. So we are also thinking about how to do that better and how to create the final, not a prototype, the final product. Any other questions?
I have a small question of your first time. I thought that it has power 30 watts and the efficiency was 40%. So like 12 watts are used actually for charging and 18 watts are going to dissipate. Where do they go? Do they go as heating or somewhere else?
The main losses are, so if we speak about the efficiency of the RF channel, what we transmit from the metasurface to the receiver coil, it is roughly 80%. And the main losses are in the power amplifier because the efficiency of the power amplifier is not that high. And the total efficiency became smaller. So it's not really proper design of the power amplifier so far. So we need to update
this is one of components, I guess.
Sorry?
This one of components, right? Efficiency of power amplifier.
You speak about the numbers?
Yeah.
Roughly 30%, something like that.
So up to 70%.
No, 30% efficiency of the power amplifier, then 80% efficiency of the RF part, and then we do have some blocks, some AC converters and AC-DC converters over here, which also minimize the total efficiency. So electronics together with the RF channel, Is it clear?
I don't get numbers, okay.
So here is your, let's say, coil to coil, here is your RF efficiency.
It was around 80%.
Around 80%. Right. Then you have DC converter over here. And here you do have some DC, then DC, and some stabilization networks, and so on and so forth. Yeah. Over here we do have roughly 30%. Over here we do have roughly 30%, and then just multiply the numbers and get the final. So this is DC efficiency means from this point to this point where we do have a load. Yeah. And this is roughly 20% something now.
All right. Do you need, like, when you test it, do we actually need to hold it?
Sorry, to
hold it?
hold?
Yeah, suppose it.
Cool down, you mean?
Yeah.
No. Powers are not that big.
And
There are some. So here is the power amplifier. Yeah. Over there, we do have a different block for that, but it is not really warm when it works.
all right.
We don't need.
Also,
It's a lamp.
Yeah, just a bulb, like a bulb.
also when you are putting devices, all devices are going to receive power equally, yeah? So this 12 watts, they are going to be divided more or less the same between all devices.
Yeah, they are more or less equally distributed.
Is it, does it depend on the diversification?
Yes, it depends. It will depend on the magnetic field profile, as your colleague has mentioned. It is not really uniform, yeah, and we do have some minima over here. So in the middle area, it will be more or less the same. If you put your device to the closer to the edge, yeah, the efficiency will be smaller.
All right. What if I put two devices on one side and one device on the other side? Are they going to still receive 1/3 of the power, or it will going to be some object distributed?
More or less equally, if you put them over here, over here.
I mean, if I don't put devices uniform.
Yeah, they will.
If some devices are going to be put close to each other, while one device is going to be put very far away from them, on the same surface, is it going to receive more power, or is it still going to be the same as passive devices on the other side of the surface?
Look, we did not study this problem in detail, yeah. So we did not study it so far because we have fabricated this demo probably 1 or 2 months ago, and now it is vacation period and many colleagues are having rest somewhere. Yeah, but look, what defines the efficiency in this term? The magnetic field, uniformity, and the coupling coefficient between the transmitter and the receiver. The coupling coefficient is more or less, it is defined by the area of your receiver coil. Yeah, so all the receiver coils are identical. It means that the same. It means that it mainly depends on the magnetic field profile. So how many magnetic flux penetrates the receiver. Yeah, in this term you define the coupling coefficient. So probably there will be some problems. Yeah, some of the receiver will get more if it's located over here. Another receiver will have less power. Yeah, but still it will be on the same order power.
All right. And one question: you mentioned 40%, and you mentioned that there's some room for improvement. How much do you expect?
I expect 80.
All right.
Yeah, 80, probably not for 2 receivers, for more numbers of receivers. Ideally have 100, yeah, but it's not real. I would expect 80% of efficiency for 3 receivers located on the board, on a smart table. I think it would be adequate. So this thing, 1 receiver will get smaller efficiency. Yeah, again, we speak about the total efficiency for all devices placed on emitters. We just simply sum up all the efficiencies. Yeah. Okay.
We also have several questions in the chat
Mm-hmm.
window. I guess the first two questions are already answered, but there is a third question from Ilya Levitsky, and the question is, do safety test results become worse if there was a metallic bracket or a ring on the head?
Mm-hmm. So there are some foreign objects on the hand that it is metallic.
Yes.
Look, we didn't test it so far. We tested just with the just a simple arm of a person over here. But our system is resonant. I believe if you do have a metallic object and the resonant of this metallic object does not the same on the frequency as your system, then it will not influence at all. You will probably get some more losses, but not that harmful, yeah. But if the metallic object on the arm is the same resonant, yeah, then it could lead to some problems. That is a good idea to test. We tested the field profiles when we just put some metallic objects on the metasurface together with the receivers. For example, some coins. And small coins, they didn't change anything in the field profiles and didn't change any story in the electric field distribution and so on and so forth. So it seems we should not expect any problems with the SAR in this case.
Okay, thank you.
But as you have very low frequency, like very long wavelength, it means that some calls or watches, they will not get any, they will not raise any problems.
Yeah.
Because,
the wave does not feel them. Yeah, it's really small objects in comparison to the wavelength. So.
And related to resonator effect, because the length of the circuit is small.
Yeah, but if you will probably put not a bracelet or something which contains metal and have the same resonance frequency, yeah.
But resonance frequency depends on the length of the circuit, which can be.
Yeah, sure. You speak about the bracelet. I speak about some foreign object which is made of metal and has the same resonant frequency. I don't speak about the design and shape of the object, yeah? So it can be that some foreign objects will influence the performances and will kill all the needed effects and so on and so forth. It will damage the system. Can be.
We have one more question in the chat from Artem Krasilov about materials and their cost. Which did you use in your prototype?
Yeah, so for prototyping, we used, for prototyping of smart table, we used the FR4 material. It is very cheap. And it is the standard PCB technology, which is roughly used everywhere. And the components which we mounted, they are not very expensive as well. So we can probably use better materials like Rogers with the lower losses, the electric losses. So we can use better capacitors for the product already. Yeah. But up to now, for the prototyping, we use rather cheap because we need to prove the idea first, yeah? And then invest more money in the in the pure fabrication process.
Thank you. So I guess that's all for today. Thank you, Polina, for the interesting presentation.
Thank you very much.
I also want to thank you all the listeners for interesting question and discussion. So see you. Goodbye.